Before 1960, the Aral Sea was one of the 4 largest lakes in the world and covered 68,000 square kilometers. It was supplied by the waters of the Amu Darya and Sir Darya rivers, and the soil nearby grew a lush variety of plants. But during the Soviet era, fields of cotton and rice took over the region, using most of the waters of these rivers and their tributaries. And by the 1980s, only a trickle of new river water made it to the Aral Sea, so it began to shrink. As the liquid water molecules evaporated, they left behind all the salt that had been dissolved in this water. This salinization covered the newly exposed soil in a salty white crust, which then blocks plants from being able to absorb water and nutrients. In the nearby fields, Aral seawater would still be pumped in for the crops, but rapid evaporation continued to leave behind a thick crust of salt on the soil. So the sea was being destroyed to grow crops, but the crops couldn't grow because of more salinization. As the Aral Sea continued to shrink and more sediment was exposed, the salt and dirt, along with fertilizers, pesticides, and other pollutants that built up over time, whirled into massive dust storms and were transported far and wide. All that stuff eventually spread over thousands of square kilometers and endangered valuable cotton and other crops elsewhere in the region. And what once was a fertile area by the Aral Sea looks like a desert with scrubby vegetation and a salty crust coating the land. The destruction of the Aral Sea has been called the worst environmental disaster of the 20th century. And one moral of this real-life parable is that the soil is a living, dynamic, and precious substance that's deeply affected by how we manage our land and resources. With the right composition, care, and natural cycling, soil supports entire ecosystems. So we shouldn't take it for granted. I'm Alize Carrere, and this is Crash Course Geography. Soils bring together all 4 spheres of physical geography, and understanding soil composition is kind of like baking. Like a rich carrot cake that needs just the right amounts of flour, water, spice, carrot, and cream cheese frosting to make a delicious treat. Soils are a complex collection of minerals, organic material, air, and water in just the right proportions for plants to thrive. The flour in our soil cake is the parent material, rocks that are broken down by plants, animals, wind, and water. The size of these rock particles determines a soil's texture and structure. Like sandstone is very strong, so it makes a chunky, coarse, textured soil. All the non-living inorganic soil minerals come from the parent material rocks. So we usually end up with elements commonly found in rocks like silicon, aluminum, oxygen, and iron. And we get different compounds of those elements as chemical processes break down the rocks. Unlike the inorganic minerals, the organic material in soil, or humus, comes from living things like leaves and partly decomposed plants and animals. Humus supplies energy and nutrients and influences the color, texture, structure, and chemical properties of a soil and how much water and air it can hold. The organic material is like chunks of carrots and walnuts in our cake. And just like in a cake, the right amount of water and air help create the perfect texture. Let's cut a wedge of our soil cake to see how it all comes together. This slice is a soil profile with layers called soil horizons that each have different properties. On the surface is the O horizon, made of some of that humus, like extra chopped walnuts we sprinkle on top of our cake. Soils rich in humus are workable, which means they have good porosity or capacity for holding water. Below this is the A horizon, commonly called topsoil, which is like the top layer of our cake with a rich cream cheese frosting slathered on top. It has tons of nutrients and decomposed organic material. So like if we lived in a world where frosting is nutritious. The O and A horizons hold a vast hidden world of biodiversity, or all different plants, animals, and microbes that exist. In fact, a quarter of our planet's biodiversity is made up of soil organisms in the ground. Small land mammals burrow and redistribute the soil, earthworms aerate soil and improve soil structure, and microscopic organisms break down organic material, hold important nutrients, or bind soil particles together. But this teeming life in soils wouldn't be possible without precipitation, just like a cake would be dry without liquids. Water absorbs minerals in the soil and becomes soil water, carrying nutrients farther down so plants can absorb them with their roots. Any extra soil water that beads and sticks to soil particles is called capillary water, which plants can use during dry periods. But soil water doesn't stop at plant roots. It can filter down to deeper levels and keep leaching or depleting the nutrients from the topsoil. A well-made cake is moist, but also light and fluffy, so the spaces between soil particles not filled with water hold soil air, which supplies oxygen and carbon dioxide necessary for life. Below the A horizon are layers of basically all the extras from the topsoil. Certain soils have an E horizon made up of coarse sand and silt. Here, finer clay and iron oxide particles are leached and carried even further down with the soil water. This process is alluviation, which is where the E comes from. All leached materials from the A and E layers accumulate in the B horizon, which is kind of like the storage center for minerals and nutrients that get leached down. Scientists usually only use the word soil to talk about the A through B horizons. That's where plant roots are, and the layers actively change through interactions with weather, nutrients, plants, and animals. But our full soil cake is bigger. The next layer is the C horizon, or regolith, which comes from partly broken down parent material. This layer is pretty unaffected by all the stuff happening above, and finding plant roots or even soil microorganisms here is pretty rare. And the R horizon is the lowest layer, made of unbroken parent material or bedrock. It's kind of like the plate the cake sits on, if the plate were made of hardened flour or something much older than the soil. The inorganic minerals and rocks in upper layers might have come from breaking down some of the bedrock, or they could have been carried by streams, glaciers, waves, and wind from far away. A soil profile is a complicated recipe to develop, but I think Paul Hollywood would give a star baker. And maybe even a Hollywood handshake. In a non-cake ecosystem, a few centimeters of prime farmland soil may require 500 years to gather nutrients and build a rich topsoil. But from Iowa to China, Peru to Ethiopia, and the Middle East to the Americas, the topsoil is being worn away faster than new soil can form. And there are record levels of soil loss happening as of 2021. Plants can't grow, and entire economies are changing, like from the salinization of the Aral Sea. It's a hard problem that we've given soil scientists, who are kind of like doctors, and look after soils to prevent such disasters from happening again. They map and analyze soil types, determine their suitability for different uses, and lead conservation efforts using science from all sorts of fields, like physics, mineralogy, hydrology, climatology, and more. To best understand the way to protect soils, understanding the different characteristics of soil across Earth can help. Like if we could walk along the 20-degree meridian, we'd see many specific soil-forming processes as we moved between climates. We'd start in the shady cool of the Congo rainforest under a dense canopy of tall trees. In this rainforest climate, rocks break down rapidly and minerals are decomposed as part of a chemical process called laterization. We call the soil that forms laterite, meaning brick-like, because it's mostly a hardened B horizon made of iron-rich clay mixed with quartz and other minerals. In fact, it's so hard it's used as building material. Moving north, we find ourselves in the tropical grasslands, which transition into semi-desert scrub, and then the true desert of the Sahara, as there's less and less moisture. In climates like these, when there's not a lot of moisture for trees to grow but grasses thrive, the soils form through calcification. Over thousands of years, calcium carbonate leaches down to the B horizon and creates a hard layer called caliche. And more calcification happens as grasses draw up calcium from the A horizon and return it to the soil when they die. Crossing the Mediterranean Sea and heading into the Alps, the topography or shape of the land influences soil development. Like on steep slopes, water quickly flows downhill without absorbing into the soil. And because of increased erosion, soils also have less time to develop. The sun also plays an interesting role in the highland climates of the mountains. South-facing slopes in the northern hemisphere that receive the sun's rays at a steeper angle are warmer, and their soils are drier. After crossing the Alps, we reach the coniferous forests of northern Europe. Here, the soil forms from podzolization, which is a word that comes from the Russian word podzol, which means ashy. As pine needles decompose, they make the soil more acidic, which leaches out aluminum and iron compounds from the A horizon. The remaining silica gives the E horizon a distinctive ash-gray color. That was just one little stretch of one meridian, but even there, no two soils are alike. And their development and distribution depends on spatial factors like climate, vegetation, topography, parent material, and time. No matter where we are, soils are the foundation of life on Earth, from the local ecosystems of plants and animals to the crops we grow and food we eat. Good fertile soils are like gold we seek out at any risk, like planting crops in the shadows of volcanoes or in the flood zone on the banks of rivers. The UN Food and Agriculture Organization celebrates December 5th as World Soil Day, because soil should be celebrated, but also because our soils are at risk. Soils are a bridge between all four of Earth's physical geography systems, but especially the biosphere and the lithosphere, or Earth's solid realm, which forms a platform for plant, animal, and human life. The lithosphere is shaped by internal and external processes that build it up and wear it down. And we'll start exploring that next time when we look at how rocks and minerals are formed. Many maps and borders represent modern geopolitical divisions that have often been decided without the consultation, permission, or recognition of the land's original inhabitants. Many geographical place names also don't reflect the indigenous or aboriginal people's languages. So we at Crash Course want to acknowledge these people's traditional and ongoing relationship with that land and all the physical and human geographical elements of it. We encourage you to learn more about the history of the place you call home through resources like nativeland.ca and by engaging with your local indigenous and aboriginal nations through the websites and resources they provide.